Hello, I'm Paul Beckwith. Since about 2007, there's been a strong uptick in the levels of methane in the atmosphere. So I'll show you the data on this. I'll show you the radiative forcing, the amount of warming that occurs with methane compared to the other greenhouse gases. But mostly I'm going to discuss a recent paper that just came out that looks at the variation of methane with longitude and latitude and year. And it also, so it looks at the rises and it gives an indication as to what the sources might be, whether the sink, the hydroxide OH, is varying and changing the amount of, that's the scavenger or the sink of methane, whether that concentration is dropping, for example. That would allow the methane lifetime to be longer. So I'm going to look at all of these things, and this paper also relates it to the Paris Accord, the 2 degrees Celsius and 1.5 degrees Celsius values, and those, with the present rates of methane rise, even if all of the CO2 emissions went down, methane would derail the whole process unless it's not dealt with. So let's get right into the data here. Okay, so just give a little plug for my last post here. I talked about how abrupt climate change is redrawing the map. I gave a rant about what was happening, and then I had a number of videos showing the data as to how, basically climate change is affecting zones, different regions around the world in, incredibly profound ways. So this image here, if you go to the World Meteorological Organization or just Google WMO greenhouse gas concentration surge to new record, you can get this paper, this article, and down here we have the diagram which I'm showing you. Okay, so basically we've got CO2 levels increasing. This is from about 1984 or so to 2017. We've got methane, which kind of leveled off here, and in 2007 there was a significant uptick again, and we've got nitrous oxide here. Now, the daily variation, if you like, the fluctuations in the curve are shown here. So the slope basically of the curve you can see here. So what you can see is in the 80s up to about 90, early 90s, there was increases between 10 and 15 almost parts per billion per year of methane. And then there was some fluctuation here, but it dropped significantly. It dropped close to zero. And then in 2007, there was a strong uptick again. So for the last decade, we've seen a strong rise. So this is 2014. It was about 12, almost 13 parts per billion per year increase, and then about 10, and then 7.7 and 7. And that's what I'll be discussing a lot in this paper. Okay, now I want to remind you, this is the forcings, this is the amount of heating that occurs from the different greenhouse gas molecules and processes. If you Google GHG radiative forcing AR5, this brings you to the, and we're in Google Images, this brings up all the images. We want the Intergovernmental Panel on Climate Change Assessment Report 5, which came out, I believe, in 2013, was the latest one. And this is the chart here that we're looking at. Okay, so what you can see is you can see the effect from CO2. The forcing values in watts per square meter are here. This is a 0, so these things are causing warming to the right side. To the left side, they actually, this is the global dimming effect from aerosols. Okay, so if you sum all of these numbers up, you get a total net anthropogenic forcing of 1.6 watts per square meter. This number is about the order of the CO2. So the methane is here, 0.48, nitrous oxide 0.16, halocarbons 0.34, ozone here, water vapor, stratospheric water vapor from methane. So when methane is broken down in the stratosphere, it produces water, and that water is a greenhouse gas, causing a bit of warming. The surface albedo changes, so this is black carbon is making the snow darker, it's absorbing more energy, so that's in the plus column. Land use changes, you know, for crops and so on, if they're making the albedo slightly higher for some sort of crops, and then the forests that were there before, or whatever was there before, that's like a negative forcing. The aerosol direct effect and cloud enhancement albedo effect. Contrails is here. Look at the solar irradiance. Okay, this is a variation in the solar irradiance, not very significant, very, very small. So the total of all, the sum of all these, you know, 1.6. Okay, now this is on Twitter. This is my post. I usually pin the previous post on my website, and this is a tweet that something I retweeted about atmospheric methane grew very rapidly in 2014, 2015, 2016, 2017 at rates not observed since the 80s, and the implications for the Paris Agreement. So if you click on this link, it brings you to this paper, or you can just Google this title. It's an open source, so anybody can access it. Very strong atmospheric methane growth in the 4 years 2014 to 2017, and the implications for the Paris Agreement. Okay, so let's have a look at some of the key points here. Okay, so the key points: the atmospheric methane is rising. The carbon isotope ratio has become more depleted in carbon-13, and I'll explain what that means. The possible causes of the change could be increasing emissions with the changing relative proportions of the source inputs. The carbon-13 ratio will vary depending on the source inputs. Okay, so that gives you an idea of the source inputs, or a decline in methane destruction. So if the lifetime of methane is increasing in the atmosphere, then the methane burden will be larger, or both of these things. And there'll be huge consequences to the UN Paris Agreement. Okay, so before I need to talk about carbon-13 a bit. So the carbon isotope ratio is here. So we have carbon-14, which is radioactive. Okay, decays into carbon-13 and carbon-12. Carbon-13 is a stable isotope. It's 1.11% of the total carbon. So it's slightly heavier. It's got an extra neutron. So it's heavier. This is 6 protons, 6 neutrons, 6 protons, 7 neutrons. Slightly heavier by 1.11. It's 1.11% of the concentration. So the vast amount of the carbon is 98.89% of the carbon is in the carbon-12. Okay, so a couple things also that I have to show you. Okay, so where are we here? Okay, so this is the del-13 carbon, which is basically the heavy carbon to light carbon ratio, carbon-13 to carbon-12 ratio. It's actually declining. Okay, so that means there's a deficit of 13 of the isotope 13 carbon. Okay, this is for CO2, but also for methane. So here I want to show you this plot, this here. So this is the del-13 of carbon from depending on different sources. Okay, so let's talk a little bit about the different sources. Okay, so this isotope, so what are we talking about with the isotope? So carbon's made primarily, this explains it very well. Okay, if you just Google atmospheric CO2 looking at the data, it's Protons for Breakfast blog. It explains it quite well, so I'll use it. So carbon's got the 2 stable isotopes, carbon-12, 6 protons, 6 neutrons, carbon-13, 6 protons, 7 neutrons. The heavier carbon-13 is only about 1%, right? 1.11%. Plants preferentially build their cells from carbon-12 base molecules. Okay, so when plants build up organic matter, it's mostly carbon-12. There's a deficit of carbon-13. So when these plants are compressed and heated and baked in the earth, the fossil fuels that are derived from plants have a slightly reduced ratio of carbon-13 to carbon-12. So if the increase in atmospheric CO2 that we're observing is due to the emissions of fossil fuels, then we can see a decline in the ratio of carbon-13 to 12, which is exactly what we see. Okay, it also talks about oxygen depletion, right? When we oxidize, when we burn carbon, right, C plus O2 gives you CO2, the O2 is decreasing. Okay, so this is a very good explanation. Okay, so that's the key thing. So we'll go back to here and we'll show you. Okay, so this is the atmospheric CO2. It's in this range here. And then the plants, C3, different plant types of plants. C3 plants, like tropical plants, C4s, grasses and things, okay, have different ranges of del-13 carbon. This is in CO2 case, right? Coal, petroleum, biogenic, thermogenic. Biogenic is biological origin, thermogenic here. This is the atmospheric CH4 range here, okay, for the del-13 carbon, and this is the atmospheric CO2 range here. Okay, so when we see a change in the del-13 carbon, perhaps it can tell us what the source is of the carbon. It can give us some information on it. Okay, so let's continue going on here. So we've had sharp rises in 2014, 2015, 2016, 2017. The ratio, the isotopic ratio is shifting, right, is dropping. The causes of the increase could be a change in the proportion of emissions from biogenic, thermogenic, and pyrogenic. This is fires. This is the earth, deep earth, heat and pressure processes, and from biological organic matter. You know, and is it from the tropics? Is it from the subtropics? Or is the atmospheric sink of methane, the OH, declining? Okay, so that's what this paper is trying to tease out. Okay, and it talks about methane being the second most important greenhouse gas. I showed you the radiative diagram. So here's, these are the hypotheses that can happen. An increase has occurred in isotopically very negative biogenic emissions, whether from wetlands or ruminants, so livestock or waste, so dumps, organic matter disposed, or all of these. So this would increase, if so, an increase in the proportion of global emissions from microbial sources may have driven both the increase in the methane burden and the shift in del-13C, so the drop of this number. Or there could be it could be the strong rise in methane from natural gas and oil. Fossil fuel methane emissions are mostly somewhat more positive in del-13C. So this would mean there would have to be a concurrent decline in a source of carbon-13 from biomass burning, or also there could be, the sinks could be larger, and this is mostly the oxidative capacity, the cleansing power of the atmosphere, which is all about this OH molecule, has declined, and that would slow the destruction of methane. Okay, and this would be a very serious thing if that was happening. Okay, so they took air samples. There were air samples from NOAA sites. There were the Brits, Norwegians, lots of air sample sites. And now we'll talk about the results and the changes, but I'll extend this to another video. So thank you for listening